Welcome back, Chemistry 30. This is the second video in the EC1.5 section. So we left off with this electrochemical cell. So looking at the zinc anode here, undergoing this half reaction with solid zinc, produces zinc ions in solution, and in the process releases electrons. And of course the zinc ions here, we have to have these electrically neutral. So we have the salt bridge, the zinc, the two positives need to come together with the nitrate, so that makes zinc nitrate. Then over here we have the electrons coming over to here. Here we have a nitric acid solution here, so the H pluses combine with the electrons to make hydrogen gas. And of course we can't have all these negatives build up, so the sodium in this sodium nitrate salt bridge come and collect with nitrate to make that neutral as well. All right. If we look at the next page, when the cell is operated under standard conditions, the cell potential is plus 0.76 volts by using the standard cell potential 0.7 volts. The defined standard reduction potential and the equation we've seen earlier, you can determine the standard reduction potential of the zinc ion and zinc half reaction. So we look at this in terms of the reduction of the cathode and the reduction equation at the anode and subtract. So we found the overall voltage. If we look back here, we saw that it was 0.7. So that's considered to be E cell. Okay, so the voltage potential difference in here is that. And of course we know that hydrogen there is considered to be 0 at the cathode. So remember, this is the anode, cathode. So we consider this to be what's happening finally. This is considered to be the initial. And of course the change is always final minus initial. So we defined this reaction here to have a reduction potential of 0. So therefore, if we are looking for what's going on at the anode, we would see that subtract and then subtract, we get it to be negative 0.76. Thus, a standard reduction potential of negative 0.76 volts can be assigned to the reduction of zinc ions going to zinc solid. Now we write the reaction as a reduction, even though of course we know that it is actually oxidation that's going there. We're losing electrons, right? So over here you can see we are losing electrons here, so we know this is oxidation technically over here, even though we're talking about reduction potentials. And over here we have reduction. So of course we always remember that because we're losing electrons. Here we're gaining electrons, Ger and Leo, but it's common practice to write it as a reduction. So whenever we assign an electric potential to a half reaction, we write it as a reduction, just to be consistent throughout everything. And it'll work out. When we apply this equation, final minus initial, it'll work out fine. Half reactions, however, are reversible, being able to operate as either reductions or oxidations. Consequently, half reactions are sometimes written with two arrows between the reactants and products as in equilibrium reactions. But if you take a look at these charts, they're just simply written as a one-way reaction in terms of reduction. So you can see all the electrons are on the left-hand side, indicating reduction. Standard reduction potentials for other half reactions can be determined in a fashion analogous to what we just did there. So seeing again what happens when it's with the hydrogen. Table on the right lists some standard reduction potentials. A more complete one is found on the Appendix E, which I borrowed from a textbook. So you'll get a copy of this, which has a whole list of many different reduction reactions. These standard reduction potentials, often called half-cell potentials, can be combined to calculate E cell values for a large variety of electrochemical cells. So we can just simply look at the combinations off here and put them together. All right, so if we look at the next page, because electrical potential measures potential energy per unit of charge, standard reduction potentials are intensive properties. So that means they do not change. when the amount of matter changes. Sorry, that's kind of messy. In other words, if we increase the amount of substance in the redox reactions, we increase both the energy and the charges involved. So since we're increasing both the energy and the charges, we're not changing anything because it's always a energy per charge calculation, right? Thus, changing the stoichiometric coefficient in a half reaction does not affect the value of that potential. For example, E reduction for the reduction of 10 moles of zinc is the same as that for 1 mole of zinc. So what we have here, so if we're multiplying by 10, multiplying by 10, multiplying by 10, because this is originally 1, 2, 1, 10, 20, 10, it works out to be the same because we're increasing both amounts as well. So let's take a look at an example here. So for the zinc copper electrochemical cell studied earlier, we have this scenario here. So we have 2 half cells going on. Given the standard reduction potential of zinc ions to zinc solid is negative 0.76 that we looked at earlier, calculate the E reduction for the reduction of copper going to copper. So copper ions going to copper solid. So what we should do here is just kind of envision what's going on here. So we know, so here we have the zinc going to zinc ions. So we know, of course, that that is oxidation. And that occurs at the anode. So I'm just going to, oops, anode, there we go. Almost wrote 2 D's. So anode, so we have zinc going to zinc ions, and in the process releasing 2 electrons. Okay, so that is the oxidation. So of course we know that is oxidation. Well, let's put LEO, lose electrons oxidation. And of course over here we have copper ions becoming solid copper. So that is at the cathode. So we have copper ions, and they're going to pick up the 2 electrons and make copper solid. And of course that is the GER, gain electrons reduction. Alright, so we have that sorted out. So now we can look at E cell. And of course we look at the 2 reductions. So the reduction at the, now what happens, so we go from anode to cathode. So cathode is where they end up finally. So E reduction cathode minus E reduction anode. Then we'll be able to figure everything out. So we know that the E of the cell, overall what happens is it's at 1.10. And we're looking for this. We're looking for the reduction at the cathode. Okay, yeah, so that's what we're looking for at the cathode. And earlier we determined that this was minus 0.76 volts. I'm going to write the V in here. It's 1.10 reduction at the cathode. Minus and the minus is a plus. So plus 0.76 volts. So of course to solve for the cathode, minus 0.76, minus 0.76. And of course this will cancel on this side. So that'll leave us with E reduction at the cathode equals that, which works out to be plus. It doesn't hurt to write down the plus, even though, yes, I know writing 0.3 implies that it's positive. It's a good idea to do it anyway. Alright, so there we go. Let's look at another example. Cell standard electron, the cell's potential is 1.46 for a voltaic cell based on these half reactions. So here we have something that's losing an electron, so of course that's happening at the anode. Something that's losing electrons to the external circuit. Then over here, something that's gaining electrons. That's happening at the cathode. So of course we know that that's going on here. So yes, at the anode we have loss of electrons, oxidation. The cathode we have gaining electrons, reduction. Using the standard reduction table, using the standard reduction table, calculate the reduction for the reduction value for the reduction of IN3+ to IN1+. All right, so I think we can find these on our table here, seems to me. Let's see here. Do I need to use the back of the book one? I might have to. Yes, I don't see it on this previous page. I don't see it here, so we're gonna have to look back. Look at the big sheet. So let's look at the big sheet and see what we got going on. So over here, let's see if we can find it. Oh, actually, I know what's going on. We're looking for that one. Here I am trying to find it, but we're looking for this. So we don't know this value. Okay, so let's back up the truck. So let's write down the equation E cell, because we're told what E cell is. Overall, it's 1.46 volts. So looking for the reduction, the cathode minus the E reduction at the anode. So 1.46 volts, and yes, we're looking for what it is at the cathode. So E reduction, sorry, at the anode I mean. So that must mean we know what bromine is, so that's likely back on that sheet. Let's take a look. So bromine, let's see, there it is right there, I believe. So bromine molecule is going to bromine ions. So bromine molecule is going to bromine ions. There it is right there. So that has a value of plus 1.6. So plus 1.06 actually. Okay. So we have that. So what I'm going to do here is move this to the other side. Plus E reduction anode. So that's going to put this as a positive on this side, which is what I want. Anode. I still have that. Now you could do this all in one step. In fact, I'm sure you can. And then, yes, subtract 1.46 from each side. And let's go over here. We'll write the final answer on this side here, because I'm running out of paper room. So when we do that, 1.06 minus 1.46 gives us E reduction at the anode is equal to minus 0.4 volts. All right, so that is how we do that. So we use those reduction potentials from the previous side to work that out. The key thing is identifying what you're given. If you're given the E potential for the cell, then you're looking for the E potential of one of the half reactions. All right, so we'll come back and we'll look at part 3 in a bit.